Venus is Earth's twin. Same size, same mass, born from the same cosmic dust. But one world became a cradle for life, while the other turned into a hell where the ground is hot enough to melt lead. So here is the question that should keep us awake at night. If Venus once looked just like our home, are we looking at our own future? When we talk about planetary twins, we are not speaking poetically. We are speaking in terms of hard numbers and physical proportions. Venus is the closest thing Earth has to a sibling, a near-perfect match in size and mass hurtling through the solar system. According to NASA's Venus fact sheet from 2024, Venus measures 12,104 kilometers in diameter, which is only about 5% smaller than Earth's 12,742 kilometers. Its mass is equally comparable, coming in at 81.5% of Earth's, making it the most similar planet to our own in terms of raw physical makeup. This is why astronomers and planetary scientists have long referred to the two as twin planets, a designation built on solid, measurable data rather than mere cosmic affection. But the similarity ends the moment you start looking at how these two worlds actually move. Venus spins in the opposite direction to almost every other planet in the solar system, a strange retrograde rotation that means the sun rises in the west and sets in the east there. This is not a minor quirk, it is a fundamental difference that turns our understanding of a normal day completely on its head. Consider the math from the same NASA fact sheet. A single day on Venus, the time it takes for one full rotation, lasts 243 Earth days, while a full year, the time to orbit the Sun, takes only 225 Earth days. So on Venus, the day literally outlasts the year, a concept so alien to our own experience that it feels less like planetary science and more like a piece of abstract art. The visual reality of Venus is just as disorienting as its calendar. If you could somehow stand on its surface and look up, you would not see a familiar blue sky or even a black expanse of stars. The atmosphere is a thick, crushing cloak of carbon dioxide laced with clouds of sulfuric acid, and these clouds are so dense that they stretch for roughly 13 to 20 kilometers in height. When the Soviet Venera 13 lander sent back its images from the surface in 1982, it revealed a world bathed in a strange glowing orange light, a permanent twilight, created by the thick chemical haze filtering the distant sun. This is the light that Venus lives under, a perpetual, eerie orange glow that makes the entire planet look like it is simmering in a furnace, a first hint that this twin is not the friendly sibling it first appeared to be. So we have a planet that is nearly our identical size, nearly our identical weight, yet it spins backwards and it lives through a day that is longer than its entire year. It sits there, a shimmering orange beacon in the evening sky, looking so much like home from a distance. It is a cosmic mirror reflecting our own dimensions back at us, yet everything about its behavior is fundamentally wrong, twisted, and alien. The real question begins to take shape in that contradiction. It is so physically similar to us, yet so fundamentally different in its experience of time and light. If these two worlds started from such similar raw materials, what happened to make one of them so benevolent and the other so deeply, profoundly strange? We have to ask ourselves why the universe took two almost identical spheres and turned them into such different homes. Imagine standing on a world where the sky itself is a furnace. The average surface temperature sits at a staggering 464 degrees Celsius, a heat so intense that lead, which melts at a mere 327 degrees, would flow like water across the rocks and zinc would boil away as vapor. If you could somehow survive the heat, the air itself would crush you. With a surface pressure of 92 bars, a force equivalent to what you'd feel nearly a kilometer beneath Earth's ocean, enough to instantly flatten a human body like a tin can. This is the reality of Venus, and yet it presents one of the most confusing puzzles in our solar system, because it's actually farther from the Sun than Mercury, whose sunlit side can reach 427 degrees, but plummets to a frigid minus 173 degrees at night. So why is Venus hotter? The answer is a thick, toxic atmosphere that acts like a blanket, trapping heat in a way that leaves Mercury shivering in comparison. It's a world where the very air is a weapon. In 1982, the Soviet Union's Venera 13 lander proved just how brutal this planet truly is, surviving for only 127 minutes before the heat and pressure destroyed it. But in that short window, it didn't just take pictures of the orange basalt-strewn surface at 457 degrees. It also recorded something we never expected to hear. The probe captured 35 minutes of actual audio from the Venusian surface, a low, rumbling sound transmitted through a microphone before the spacecraft was melted into scrap metal, marking the first and only time humanity has ever heard a hellish world come alive. And as if the crushing weight and searing heat weren't enough, the planet's upper cloud decks whip around at 370 kilometers per hour, far faster than any Category 5 hurricane on Earth, which tops at around 252 kilometers per hour, creating storms that would tear our most robust structures to pieces. This is a world where the ground glows with heat, the air is thick enough to drown in, and the winds scream with a ferocity we can barely comprehend. a place that is, by every measure, a living nightmare. How could a planet so similar to our own, a twin in size and mass, have become this? It's impossible that such a world could have ever looked like home, a place that could harbor oceans and blue skies. And yet, the evidence suggests it once did, forcing to wonder if we are looking at a vision of our own potential fate. An unrelenting blanket of carbon dioxide traps every photon of incoming sunlight, turning the surface into a planetary oven where a block of lead would liquefy within seconds of touching the ground, pooling into silvery puddles that snake across the cracked volcanic plains. The air itself is a supercritical fluid, a dense, opaque soup of sulfuric acid clouds and carbon dioxide that presses down with the weight of a kilometer of ocean, enough to crush a nuclear submarine like a soda can, and any structure we could build would implode before the heat even had a chance to melt it. Your lungs would collapse instantly under 92 bars of pressure, the air rushing in to fill the vacuum of your chest cavity with gases that would dissolve your flesh on a cellular level. A death so swift and so complete that your body would never even hit the ground, instead being vaporized into a shriek of superheated steam that mixes with the acidic haze. The difference between this hellscape and Mercury, a world that sits closer to the sun, is stark and instructive. Mercury scorched between scorching days and frozen nights because it has no atmosphere, no atmosphere, while Venus swelters in a permanent fever dream because its thick shroud of gases traps every degree, a runaway greenhouse effect that turned up a cautionary tale of how a planet can completely transform. When Venera 13 touched down on March 1, 1982, it had just 127 minutes to live, and it spent those fleeting moments transmitting 14 panoramic images that revealed a landscape of flat, fractured rocks under an orange sky, and as the temperature climbed past 457 degrees, hot enough to melt zinc, the probe's internal components began to warp, its electronics firing off final garbled bursts of data before the metal casing sagged and the whole machine slumped into a heap of molten ruin, a testament to how even our most advanced engineering is nothing more than a candle in a hurricane. Could any of us truly grasp what it means to stand on a surface where the ambient noise is the sound of your own ship groaning and cracking under the strain, where the only wind is a howling super-rotating current that circles the planet in just 4 days, moving at speeds that would fling a human body across the horizon like a rag doll? This is not a place for the living, not a place for anything that draws breath, and yet the silence it keeps is one of violent, relentless transformation. A world that has surrendered entirely to the physics of its own destruction. And as we stare at this inferno, we cannot help but feel the chilling possibility that we are gazing into a mirror. A reflection of what Earth might become if our own atmosphere continues its closed-up, insidious warming. For decades, the working assumption was that Venus was born hellish, a cautionary tale of a planet that never stood a chance. But what if that assumption is wrong, and the evidence points to something far more unsettling? A growing body of research suggests that Venus was not always the inferno we see today. Computer models published in Nature Geoscience in 2016 by a team including Way and colleagues indicated that Venus could have hosted shallow oceans of liquid water for 2 to 3 billion years. These simulations, run at the NASA Goddard Institute for Space Studies, painted a picture of a planet with a surface temperature between 20 and 50 degrees Celsius, a climate cooler than modern Earth's. That is not a scorched wasteland. That is a world with a potentially temperate climate and stable bodies of water on its surface. The models suggest this wasn't a fleeting wet phase either, but a persistent feature of the planet's early history. So, the question of whether Venus was ever truly habitable is not just philosophical. It's becoming a matter of scientific consensus. Further evidence emerged from a different angle in 2017, when researchers from the Center for Space and Habitability published a study in astronomy and astrophysics. Their modeling efforts pointed to an average ocean depth of around 300 meters on ancient Venus. To put that into perspective, that is comparable to the average depth of the Atlantic Ocean, not just a few scattered puddles, but a deep, planet-wide ocean. The implications were staggering, suggesting a water world that would have been unrecognizable from the desiccated rock we see today. But the most compelling chemical clue comes not from what is present, but from what is missing. By analyzing the ratio of deuterium to hydrogen in Venus's atmosphere, scientists found that the planet must have once possessed a massive quantity of water, a volume 100 to 1,000 times greater than what remains in its atmosphere today. This is the forensic evidence of a crime scene. The hydrogen, a key component of water, has been systematically stripped away over eons. The story does not end with a single model. A more recent study from the University of Washington in 2023, published in Nature Geoscience, used sophisticated 3D simulations to argue that Venus could have retained its liquid water for up to 3 billion years, a significantly longer window than previous models suggested. This extended timeline is crucial because it pushes the habitable period of Venus right up against the era when life was emerging on Earth. The implications are profound. If Venus had stable oceans and a moderate climate for billions of years, then the door must be open to the possibility that it was not just a habitable planet, but an inhabited one. Research by Way and Del Genio, published in PNS in 2020, strengthened this case by suggesting that Venus could have supported microbial life on its surface for billions of years, potentially until just 750 million years ago. That is not ancient history. In geological terms, that is almost yesterday. So what happened? What kind of machine could have torn apart a world that was once so similar to our own? Venus receives only about 91% of the solar energy that Earth gets, yet its surface temperature sits roughly 470 degrees Celsius higher. That single contradiction tells you everything about the machine we are dealing with. This is not a planet that is simply closer to the Sun, because Mercury, which orbits far nearer, swings between blistering heat and freezing darkness while Venus stays locked at one deadly temperature. Only one mechanism can explain that kind of imbalance, and it is the same process that keeps a car baking in summer sunlight with the windows rolled up. The atmosphere itself has become a trap, and the gas doing most of the trapping is carbon dioxide. Consider the raw numbers for a moment. Carbon dioxide makes up 96.5% of the Venusian atmosphere, while on Earth it accounts for just 0.04%. That difference is the entire story in miniature. Our world has a thin blanket of greenhouse gases that keeps us comfortable, but Venus wrapped itself in a suffocating shroud thousands of times thicker. When sunlight reaches the planet, it heats the surface, and the surface tries to radiate that heat back out into space. The carbon dioxide, along with clouds of sulfuric acid, reflects and absorbs that outgoing radiation, so the energy stays put. Every photon that arrives gets trapped, and the temperature climbs and climbs with nowhere to go. But the really terrifying part is how this process started. The runaway greenhouse effect works like a feedback loop that refuses to stop. Imagine a younger Venus with oceans of liquid water, much like Earth. As the sun brightened billions of years ago, that water began to evaporate a little more than before. Water vapor, it turns out, is itself a potent greenhouse gas, so the extra moisture in the air trapped more heat, which made the surface hotter, which evaporated even more water. Every degree of warming pushed more vapor skyward, and every additional layer of vapor pushed the temperature higher still. This is the positive feedback loop that scientists describe when they talk about a planet losing control, and once it starts, there is no natural break to slow it down. The oceans did not simply dry up, they essentially boiled themselves into the sky. The endgame was even more brutal. Water vapor drifted up to the upper atmosphere where intense ultraviolet radiation from the sun split the molecules apart. The lighter hydrogen atoms then escaped into space, carried away by the solar wind, and the heavier oxygen latched onto other elements in the atmosphere. What was once a planet of oceans became a desiccated shell, and researchers estimate that 90 to 95% of its original water was destroyed and lost forever in this way. Even today, escape continues at a staggering rate, with scientists from the Journal of Geophysical Research calculating that around 4 times 10 to the 27th hydrogen molecules leave the planet every single second. That is an almost impossible number to visualize, but think of it as the final exhale of a world that has been gasping away its lifeblood for billions of years. A 2021 study using argon isotope analysis published in the Journal of Geophysical Research revealed that the most dramatic water loss happened astonishingly early, within the first 1 to 1.5 billion years after the planet formed. That means the window for a comfortable, ocean-covered Venus shut far faster than anyone previously believed. So when you hear about the greenhouse effect in political debates or environmental news, remember what it actually did to an entire world. We're not talking about a subtle shift in average temperatures or a few extra hot days in summer. We are talking about a mechanism so powerful that it took a twin of Earth, stripped it of every drop of water, and left behind a corpse lingering at 464 degrees Celsius. The question that hangs in the air now is whether we are merely studying a distant catastrophe or staring at a warning that applies to our own future. In September 2020, the scientific community and the entire world were shaken by an announcement that seemed almost too good to be true. A team led by Professor Jane Greaves published a paper in the journal Nature Astronomy claiming the detection of phosphine gas in the clouds of Venus, a molecule that on Earth is primarily associated with biological activity. The concentration was reported at 20 parts per billion, and the news exploded across every news outlet, dominating headlines and igniting public imagination with the possibility that we were not alone. It was a dizzying moment, the kind that makes you feel like you are living through a pivotal chapter in history. But then, the machinery of science did what it does best, which is to question everything. In 2022, researchers at Cornell University presented a rigorous counter-argument suggesting that the signal detected by Greaves's team could be explained by sulfur dioxide, a common and completely non-biological gas in the Venusian atmosphere. The initial excitement was tempered by this sobering reality check, and the euphoria began to fade as the scientific community engaged in a thorough and sometimes heated debate. The phosphine story wasn't a simple collapse, though. It was a demonstration of the self-correcting process that makes science so powerful, a process built not on stubbornness but on relentless verification. The lesson here is not that the detection was a failure, but rather that the system worked exactly as it was designed to, filtering out initial errors in the pursuit of a more accurate truth. So, if the surface is an absolute hellscape, where does that leave the search for life on Venus? The answer might be found high up in the sky, far above the crushing pressure and melting heat. The clouds themselves, despite being composed of concentrated sulfuric acid, occupy a region where temperatures are remarkably temperate, ranging from 30 to 70 degrees Celsius. This zone, as suggested by research from Arizona State University, could theoretically provide a stable environment for microbial life, a habitable layer floating in an otherwise deadly world. And this isn't just speculative fantasy. In 2020, a team of astrobiologists discovered that certain species of bacteria on Earth can survive in an 80% sulfuric acid solution, a hostile environment they tested directly in the lab. This brings us to a crucial skill for navigating the modern information age: how to distinguish real scientific findings from sensationalized noise. The first step is to always check the source, favoring peer-reviewed journals like Nature Astronomy over clickbait websites that prioritize emotion over evidence. Second, look for corroboration. A single, unreplicated result is always a tentative one, while a finding that has been validated by independent groups carries considerably more weight. And when a discovery is announced, be patient and wait for the scientific community to test the claims, because as the phosphine story shows, the subsequent debate is not a sign of weakness but the very heart of how knowledge advances. The global media frenzy that erupted in September 2020 was unlike anything astronomers had ever witnessed. Headlines screamed about alien life, and for a few weeks the line between groundbreaking discovery and science fiction blurred completely. Yet, within the hushed corridors of observatories worldwide, a quieter, more rigorous conversation began. Other teams scrambled to reanalyze their own archival data, and slowly, the cracks in the phosphine narrative began to show. A newer, far more detailed analysis suggested that the signal might have been misattributed, its true source being sulfur dioxide, a common atmospheric compound on Venus. The initial blast of excitement cooled into a sobering realization. They had been looking at a ghost in the data. This dramatic reversal wasn't a failure. It was the scientific method working precisely as it should, a self-correcting mechanism that values verifiable truth over tantalizing possibility. To truly harness the lessons from this celestial whodunit, one must be willing to sit with uncertainty. The next time you encounter a sensational claim about the cosmos, let the phosphine roller coaster be your guide. Pause before you share the news and ask a simple, powerful question. Has this finding survived the brutal scrutiny of the scientific community, or is it a solitary signal still waiting for validation under the harsh light of independent investigation? The answers we find there, whether they reveal life among the clouds or simply a beautiful, lifeless chemistry, will forever alter our cosmic perspective. The most unsettling comparison begins with a single number. Carbon dioxide makes up 96.5% of the Venusian atmosphere, while here on Earth it constitutes a mere 0.04%, a difference so vast it feels like comparing an ocean to a single drop of rain. That overwhelming blanket of gas is the engine of a runaway greenhouse effect, a process that turned a world with oceans into a permanent hellscape. What happened on Venus is not a slow, gradual decline but a swift catastrophe, a planetary fever that spiked and never broke. And standing here, staring at that fate, we have to wonder about our own trajectory. The warning from our twin is stark, but it is not a prophecy we must accept blindly. The mechanics that destroyed Venus are understood, and while we pour carbon into our own sky at an unprecedented rate, the crucial difference is that we see the cliff edge approaching. This is where the story turns from pure dread to a more active, engaged curiosity. Because the scientific community is not just wringing its hands, it is building the tools to look closer. NASA has confirmed the Da Vinci mission, slated to plunge a probe through the planet's thick atmosphere to measure noble gases and understand how it formed and evolved. Alongside it, the Veritas mission and the European Space Agency's Envision will map the surface and study its geological history, all scheduled to launch around 2031, promising to rewrite what we know about our siblings' past. This relentless pursuit of knowledge is not new. It is the culmination of nearly 60 years of trying. In 1962, Mariner 2 became the first spacecraft to fly past Venus and radio back the shocking truth of its searing heat. Decades later, in 2020, the Parker Solar Probe swung by the planet, detecting natural radio emissions and offering a fresh perspective on its atmosphere. Each mission has peeled back a layer, moving us from simple observation to complex understanding, and the upcoming fleet will do the same, turning a distant horror story into a closely studied case file. A 2023 study in Nature Geoscience suggests the planet may have shifted from a wet world to its current arid state in a span of just 2 billion years, a blink of an eye in cosmic terms. So how do you keep track of this unfolding story and the lessons it holds for our own world? It is simpler than you might think. You can follow the official NASA and ESA websites, which announce each milestone and publish the raw data as it comes in. Space agencies are surprisingly open, and the press releases they issue are written for the public, not just for academics. When Da Vinci plunges through those clouds, you can be there for the descent in real time. Paying attention to these missions is not just a hobby for science enthusiasts. It is a way of acknowledging that the future is not written in stone, that the fate of a planet can be altered. That is the hidden hope buried in the tale of Venus. It is a warning written in fire and acid, a testament to what happens when a climate system tips over a point of no return. Our twin sister burned because she could not stop herself, but we have the advantage of foresight. We know the trap exists, and we have the ability to change course. The question that hangs in the void is not whether Venus can teach us, but whether we are willing to listen before the lesson becomes too painful to survive. We began with a twin, a near-perfect mirror of our world in size and mass, a place that may have once held oceans and a mild sky. That sibling is now a furnace, a vision of what happens when a climate tips past its point of no return, and the warning it carries speaks directly to us. The story of Venus is not merely a tale of a distant planet, it is a chapter in our own possible future, written in advance. We looked at our sister world and saw a fate we could recognize, a path our own planet could follow if we ignore the signs. The transformation may not always be slow, and it is certainly not guaranteed to be reversible. Our twin perished because its atmosphere became a trap, a runaway greenhouse effect that boiled away its oceans and left behind a wasteland of crushing pressure and sulfuric clouds. Here on Earth, we are adding carbon dioxide to our air at a rate that has no precedent in the geological record, and the comparison between our Mon's 0.4% and Venus's 96.5% should not offer comfort but a stark warning. We still have time to choose a different outcome, but that time is measured in the coming decades, not in the distant eons of planetary history. The missions we are sending to Venus, the Da Vinci probe that will plunge through its atmosphere, are not just scientific curiosities. They are our attempt to read the final chapter of a cautionary tale. As you go about your life, consider that the power to shape our own ending rests in the small, daily decisions we all make. Our sister world is dead. Will we awaken to change our own fate before it is too late?